Hi everyone, welcome back to Edu-Malanga if you're joining us again. If you are joining us for the first time, welcome. On Edu-Malanga, we develop video tutorials that cover the Matric syllabus of South Africa. Welcome to today's tutorial. We're working on the third unit of the year, and this unit looks at exponential and logarithmic functions. Today we are doing the first example of exponential functions. We have already introduced this topic in 2 other videos, so if you're not familiar with exponential functions, I suggest you go back and watch those videos. Not only will you be able to understand exponential functions, but you'll also be able to understand exponential laws. So let's get into our first example on this unit. In example number 1, we're given a function, and the function is y is equal to 2 to the power of x minus 1 plus 5, and we're asked to answer the following questions on that function. First, we're asked to draw the graph of this function. Then we're asked to determine the horizontal asymptote of the function. After that, we're asked to draw the graph of y is equal to 3 times 2 to the power of x minus 1 plus 5. And the last question they ask us is, explain how the coefficient 3 has affected the behavior of the graph. Okay, let's get started. We'll start by answering question 1, where we asked to draw the graph of the function. Question 1 will be answered here. I'm going to rewrite the formula, which is y is equal to 2 to the power of x minus 1 plus 5. And on this table over here, I'm going to write all the values that go on the graph. We're going to have x, which is all the domain values. Then we're going to have y, which is all our range values, and we're going to use the formula here to determine the y values from the x values. Let's get started choosing values of x. We're going to start from minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. So these are the values that we're going to plot on our graph. What we're going to do now then is we're going to substitute in x values in this formula and then solve in order to determine the values of y. This is the part where you have to use your calculator, guys. I suggest you pause this video and solve for the y values. How you do this is whenever you see x, you substitute the value that you have over here. So for example, for negative 4, you're going to have y is equal to 2 to the power negative 4 minus 1 plus 5. Plug this into the calculator and you'll solve for y when x is negative 4. And then you do this for the rest of the values. I've already done this beforehand, so I'm going to fill in the values of y. You may check your values against mine. So when x is negative 4, y is equal to 5.031. When x is negative 3, y is equal to 5.063. When x is negative 2, your y is 5.125. For negative 1, you get y is equal to 5.25. When it's 0, it's 5.5. And then when your x is 1, you get y is equal to 6. When it's 2, you get y is equal to 7. When it's 3, y is equal to 9. And the last values of our domain and range that we'll solve for is when x is 4, y is equal to 13. So these are the values of x and y for this graph. Let's draw it now on the graph paper over here. We'll start by drawing the y-intercept, which is when x is equal to 0. So it's at this point. When x is 0, y is 5.5. So let me put it on the graph. 5.5 would be about here, which is halfway between 5 and 6. And let's go towards the negative. We have 5.25 for negative 1 and 5.125 for negative 2. Okay, so this was 5. I'm going to estimate. That's all I can do. Okay, and when you go to negative 3, the values are getting even smaller. You get 0.63 and 0.31. So let me go even smaller and even smaller. And let me go to the positive side now. When your x is 1, y is 6. And when your x is 2, y is 7. Okay, when your x is 1, so x is equal to 1, y is equal to 6. And when your x is 2, y is equal to 7. Okay, let's continue. When your x is 3, y is equal to 9. And the last one again is when your x is 4, y is equal to 13. So let's draw those. When your x is 3, y is equal to 9. And when your x is 4, y is equal to 13, which is about there. Let me draw this graph now. Start over here. And I'll also label it. This is the graph of y is equal to 2 to the power of x minus 1 plus 5. So we've solved for the first question. The second question asked us to determine the horizontal asymptote of the function. So let's come back to our values. As x gets smaller, we can see that we have 5.031. So what we're going to do is we're going to pick an even smaller value of x. So for example, let x equal to negative 10. Let's substitute this into our equation. So the equation will become y is equal to 2 to the power of negative 10 minus 1 plus 5. Again, plug this into your calculator and the answer that you'll get is 5.00049. So as your x values become large negative numbers, you moved from negative 1 all the way to negative 10. What we're noticing is we're getting closer and closer to 5. This is also visible on the graph. The function is drawn above the line y is equal to 5, and so the horizontal asymptote is equal to y is equal to 5. This is the line that represents our horizontal asymptote. So we've now answered the second question. Let's move to the third question. The third question asks us to draw the graph of y is equal to 3 times 2 to the power of x minus 1 plus 5. This function is very similar to the one that we solved. The only difference is that the 2 has been multiplied by a coefficient of 3. Let's solve for the same domain and range values for this function. We'll again rewrite the equation. Y is equal to 3 times 2 to the power of x minus 1 plus 5. Here we're going to have our x values. Over here we're going to have the y. We'll again start with minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, and 4. Again, I suggest you pause and use your calculator to substitute in the values of x and solve for y. I've already done this beforehand, so I'm going to just write down the values. For this function, when x is negative 4, the y is 5.094. When x is negative 3, it's 5.188. And when it's negative 2, it's 5.38. When it's negative 1, you have 5.75. And when your x is 0, y is equal to 6.5. When you have 1, you get y is equal to 8. For 2, your y is equal to 11. For 3, y is equal to 17. And lastly, when x is equal to 4, y is equal to 29. So we're going to draw this function on the same graph where we drew the function where y is equal to 2 to the power of x minus 1 plus 5, but we'll use a different color. So let's get started. We'll again start with the y-intercept value. When x is 0, y is 6.5. So let's plot that over here, 6.5. We're now here, and we'll move to the negative side. When x is negative 1, you have 5.75, and when you have negative 2, you have 5.38. Let's plot that. 5.75 would be approximately here, and 5.38 would be approximately there. The next values are when x is negative 3, y is 5.188, and when x is negative 4, y is 5.094. So it's getting smaller and smaller and closer to 5. Let's estimate. We'll just keep estimating. Now let's move to the positive side. When x is 1, y is 8, and when x is 2, y is 11. X is 1, y is 8, x is 2, y is 11. We can't represent the values for when x is 3 and 4 because our graph ends at 13 approximately, but we have enough values to draw the graph, so let's draw it. Go like this, I suspect, and this is the graph of y is equal to 3 times 2 to the power of x minus 1 plus 5. We've just answered question 3. The last question asked us to explain how the coefficient 3 has affected the behavior of the graph. Let's look at this graph. Essentially, we have this graph, and all we've done is multiply it by this coefficient, which is 3. And what we see is that the graph seems to be rising even more steeply. So let's explain that in our answer. Question 4. See, the graph is rising more steeply. This question gives us an opportunity to understand the effect that a coefficient has on a graph. So for example, if you have a graph y is equal to a to the power of x, and then you multiply a by a coefficient, and it becomes y is equal to c times a to the power of x. This coefficient, when it's a positive whole number greater than 1, then for c greater than 1, the graph rises more steeply. Just as we saw in our example, our coefficient is a positive whole number that is greater than 1, and we can see that the graph is rising even more steeply. When 0 is less than c, which is less than 1, so when your c is a fraction, say for example we had c is 1 over 3, then what would happen is the graph rises less steeply. I'm going to draw just an approximation on this side. So what would have happened is our graph would have been over here, and it would have opened up and risen less steeply, and this would have been for when 0 is less than c, which is less than 1, meaning that our coefficient is a fraction. So this is a general rule for when you're looking at exponential functions and you have a coefficient multiplying your exponential expression. We've reached the end of our example, and we've also learned a new general rule. I hope you understood everything that I have explained. If there's anything that confused you, please may you leave me questions in the comments. I'll try my best to respond to them.